So that's the branch along X-ray. The X-rays we are going to have will have so many energies based on the site of interaction of the electron with the nucleus. So that's the one form of radiation we can have. The second one is the characteristic X-ray. Characteristic X-ray. Which we know by the name characteristic. It is based on this characteristic of each atom. The different atoms have a different characteristic energy ranges based on, of course, the things we already know. You have a nucleus, of course, you have so many orbital electrons interacting. At the end of the day, you have electron moving, so many of them moving. If they eventually interact with, of course, this interaction we have learned about interaction. So many interactions occur. You can have Rayleigh scattering, you can have Compton scattering, you have photoelectric emission. So many of them. Assuming we now have photoelectric effect happening around here, moving this electron, we are going to have a cascade of electrons, this one falling here, a vacancy here, this one, and so on and so forth. So these transitions will actually give us a characteristic X-ray. So these two portions of X-ray, they are what we use. They are the X-rays that actually come out from the X-ray tube. But for this, like I said before, for mammography, which is a special X-ray.
Excuse me, sir.
Okay.
Please, can you go over the characteristic X-ray production again? Sorry.
Okay, no problem about that. I said the characteristic X-ray has got to do with electrons interacting with the fired electron, because X-ray production has got to do with, I'm going to go into that later. It's actually when you heat up a filament. When you heat up the filament with energy, with electrical energy, something will become hot. As it becomes hot, electrons will be emitted through a process called thermionic emissions. Electrons will be emitted. As they are emitted, they will flow towards the cathode. After this, we're going to look at that process. We're just using this to explain the different types of X-ray that we get from our X-ray machine. So characteristic X-ray has got to do with the electrons interacting with the orbital electrons, not the nucleus or the nuclear region. The nuclear region interaction of electrons will give rise to Bremsstrahlung X-rays, whereas the interaction of these fired electrons with these orbital electrons, when this one comes, you can knock off this and leave a vacancy here. The vacancy will now be filled with electron from the upper shell. When that happens, the difference in these two shells, the energy levels of these two shells will now appear as a form of radiation, X-ray radiation, which is the characteristic. I said the name characteristic is because, for example, this is a K shell, this is an L shell. For tungsten, the difference in K and L is a characteristic of tungsten. It's different from molybdenum. If an electron falls from L shell to K shell in molybdenum, the energy is a known energy. If it is tungsten, the energy is a known energy, L to K. Likewise, M to L or M to whatever. It is a known energy. So it is characteristic of that atom or that element. So that is why it is called characteristic X-ray. So it is just the interaction of this electron with the orbital electron. And of course, we also have so many things happening at the same time. You have electrons being fired, so many things. You could also have Compton scattering. The Compton scattering will also give us a form of an X-ray, photon, which will be scattered. So many things actually happen inside the X-ray tube. But a major form of X-rays are the ones that are produced as a result of X-ray, Bremsstrahlung lung, and as a result of characteristic X-rays. Those are scattered photons, few of them still go out through the X-ray tube, which also eventually form part of the X-ray that we use for imaging. So having said that, we want to look at the principle of X-ray production, the principle behind it. X-ray production, we can actually produce an X-ray in various homes, but it is not going to be as energetic as the one we use, because of course we wouldn't be able to get to the potential difference that is normally used in the production of X-ray. We are talking about something from 20,000 volts to around 150, 200,000 volts, which is a way greater than the ones we can handle at home. Of course, for simple uses, we use direct current, not even alternating current. So the principle involves the cathode. We have a cathode, which essentially is a wire that is connected to an electric source. And then you have, when you now heat up this electron, you heat up this filament, which is a cathode. If you heat it up through electricity, like we all use gas, electric pots, kettles, and so on and so forth at home. Some of them they have filaments. It's just as simple as that. So if you heat up this filament, you're gonna have, it is at a particular point in time. In fact, immediately you start heating, this one starts giving off electrons, and the electrons will now begin to percolate around here. Will now begin to percolate around here until you have space charge and saturation. You now have so many of the electrons here. You have another portion, which is the place we want to direct the electrons, which is called the anode. If you don't apply any potential between here and here, nothing happens. The electrons will just be here. They'll just percolate around here. Nothing happens. But immediately you apply a voltage between these 2 points. Let's say you keep this one at a voltage of 1 volt and this one at a voltage of 3 volts. The potential difference is 3 minus 1, which is 2 volts. So because of that difference in potential, electrons will now begin to move towards this area because of the potential that has been introduced. That's just a potential difference. And the more the value of this potential, the more the velocity, the more the rate at which these electrons that have percolated here will begin to stream to the cathode, to the anode. This is a positive electrode, positive. This is a negative electrode, which is a cathode, this is an anode. So when the electrons arrive here, what we had explained there before, they begin to interact with the atoms of this anode. As they interact, we're going to have a Bremsstrahlung X-ray, and we are going to have a characteristic X-ray. At the end of the day, we have this interaction. We're going to have a production of X-ray. Energetic photons, X-ray will now be produced. Then you have some collimators, which will now define the size and the shape of the field that you are getting. Maybe 2 by 2 millimeter, 2 centimeter by 4 centimeter, as the case may be, depending on the anatomy one wants to, the technologies want to image. If it's something that requires wider distance, the collimators will be opened more. So the whole of this is usually must be enclosed in a vacuum, and the vacuum is there such that, what's a vacuum? A vacuum is just an empty space, a space in which everything has been evacuated. Every air has been evacuated, every gas has been evacuated. As you continue to suck out air from this, you begin to increase the potential, the vacuum. You begin to reduce the number of air inside. we are getting, at some point, we're going to get a near vacuum. We cannot actually get a perfect vacuum. It's almost impossible, but at some point in time, you're going to have a somewhat empty space. The vacuum is so needed such that when the electrons are streaming towards the anode, it will begin to hit the air particles. Because if that happens, it's also going to introduce some form of X-rays, which I mean, of course, some form of interactions, which will eventually release some type of photons, some type of X-rays, which we don't actually need. So we need that to be evacuated. So it's just the simple principle behind that. And again, we usually have a filtration. We, for the ordinary spectrum of X-ray, we have something like this. The ordinary spectrum, maybe spectrum goes this way. That is from the this energy increases. Going to increase this way. The ones here, this is the maximum energy. Assuming you have a potential of maybe 100 kV, is going to be at 100. That is the electron. The electrons are at a potential of 100 kilovolts. The maximum energy of the photon, any photon there will be 100 kilo electron volt. That's the maximum energy. Can have any energy from this range. This is the unfiltered section. But in X-rays, in all X-ray equipment, we normally introduce a filtration, and the filtration can come in form of both inherent and added filtration. I think we are going to get to that later. But essentially, what that does is to actually make this to actually change the shape of this spectrum, so that the low energetic and this low energetic portion, because we have so many of them, we have so many of these low energetic portion. You can see at this point, this is actually the intensity or the number of number of photons, number of photons. We have so many of them here. Here, as the energy continues to increase, the number of photon continue to decrease. So these are lower energetic ones. There are so many of them. So we need to remove them. We need to remove them by application of some filters. So when that comes, the shape of this thing is going to be modified based on what we want. Remove these low energetic, remove them as much as possible, that their numbers have been reduced. So that is done just to protect the patient, because if you don't do that, these low energetic photons, X-rays, will, of course, don't add any value to the image quality. What they do is just to introduce unnecessary dose to the patients, which is not what we want. So let me share another diagram with us to further throw more light on this. Um, we can actually use this. This wasn't what I actually wanted, but we can still use this. This the initial without the energy without iteration comes up here and goes down this way. Comes from up here and goes down. But when we introduce the filter, this is now the shape. When we introduce the filter, those low energetic portion would have been reduced. As if we want to reduce from 0 to 10 kiloelectron volts. So we don't have any, this one will substantially remove, the filter will substantially remove from this energy to this energy. So that what you have is from 10, which is not so. But if not with that, we don't do that. We have so many of these portions down this area, and so on and so forth. Then we have some characteristic resistance spikes here. These are the contribution due to characteristic emission. This, of course, is imposed on the Bremsstrahlung long spectrum. This one, K alpha 2, K alpha 1, and so on. They are just different portions of the characteristic X-ray. The X-ray, the characteristic might be as a result of transition from L shell to M shell, L shell to K shell, we have alpha, or from any other shell to a K shell, alpha 2. Then, of course, can have so many of them, so many alphas. And then if the shell is a distant from K, maybe M, N, and so on and so forth, we are going to have a beta 1 characteristic emission. It happens at a particular energy, which you can trace down. Very, very particular energy, which you can trace down. You can see this, see the energy close to 60 kiloelectron volt. This one is around 65, and this one is around 69 or so. So they haven't defined them energy, whereas in the spectrum, the Bremsstrahlung spectrum is a spectrum of energy from the least energy to the maximum energy. You can have that. If you add further filtration here, you might want to reduce this filtration. You might want to remove 0 to 20 kiloelectron volt. All you need to do is add some thickness again, which we now modify this one to start from here, kind of go up. So filtration is there to remove the low energetic electrons, which we wouldn't want. Then another factor that determines, which we're going to see that much later, the major factor that determines X-ray production. That determine X-ray production. The two factors are just the atomic number of the target atomic number of the target and the kinetic energy. Kinetic energy of the electrons. The duration of X-ray is directly proportional to the Z number. The elements with high Z number are preferred to elements with low Z number, because the elements with Z number, high Z number, will give us a very, very good portion of Bremsstrahlung. That's a very, very good amount of Bremsstrahlung radiation, whereas the one with those Z materials wouldn't do that much. So we're not going to have so much energy because of that. So that is why we normally use tungsten. It's around 78, 78 tungsten. Tungsten is a good material for the target. The target is actually the anode, whereas the cathode is the electron, where the electrons originate from. Okay.
Sorry, we can't see the board again.
Oh, I didn't stop the share. So sorry about that. So sorry about that.
No problem.
Okay. I said the factors that determine X-ray production are majorly the atomic number of the target and the kinetic energy of the electrons. If you have the atomic number of targets is such that we want an element that will give us a good amount, a generous amount of X-ray production. That's a good amount of brenstalone, and it is we have tungsten, the material that have high Z element has high Z number, high Z, that is high proton number. The elements down there, they are the ones that will give us a good amount of X-ray production. Why? Because an element that is an element that has so many number of protons and neutrons, the probability of interaction of electrons with them will be high. And of course, if the probability of interaction of electron is high, it means that we are going to have so much more Prince-Along X-ray, and of course, so much more characteristic X-ray. So this one is prepared to low Z material. That is one. And of course, we have reasons for that. In mammography, the preferred materials are usually molybdenum and rhodium. They also have high Z material, but they are not as high as tungsten. Tungsten element W, they're not as high in atomic number as tungsten. Just for us to have some minimal amount of energy, because in mammography we are looking at using energy from say 15 kiloelectron volts around 30, 40 kiloelectron volts, whereas in general radiography we are looking from 40 kiloelectron volts, that's 40 kilovolts, to around 150 kilovolts. We always see that on the operators and manual, the operators and console. And this the energy rate. Some actually start from 50 to 150 and 40 to 150. So we have that high energy gap. Whereas for mammography, it's just around 15 to 60 because of the low Z number, which will give rise to lower energetic X-ray, which is actually what we want, what we need. Okay. So then the kinetic energy of the electron determines how fast the electrons will impinge on the neutrons. It increases the kinetic energy of the electrons. We are going to have faster production of an X-ray. You can't compare electrons moving at in which the potential is maybe 20,000 volts to the one that's the potential between the cathode and the anode is 200 volts. This one will arrive will be moving faster, as because of that we are going to have more production of X-ray. So the more the potential between the cathode and the anode, the more the number of X-ray photons, X-ray quanta we are going to have. So all these should at times I ask myself, why do we need all these engineering and physics nuances? Some of us might want to go into private and practice when we. So it is good for us to know these things. When an engineer or a physicist is talking, I want to change this portion. I want to change the generator. I want to change this tube. The tube is old. Blah blah blah. Gas has percolated inside. The vacuum has been compromised. Blah. One should be able to flow along. If not, one might be ripped of some fortune. So all these things are very, very important. I remember in a particular school when a boy went home to tell his parents that he broke a paramecium cadatum. You can imagine that. His parents came begging that, how are we going to, my son said he broke this thing, please, how are you going to help us out? Unfortunately for the guy, the parents met the teacher. The teacher started laughing. But the guy, anyway, he received some generous amount of flogging. So we should know what we are going into, so that at times we want to be at a particular page with some of these engineers, physicists, or whosoever. You might want to know the type of shielding that should be adequate, and that when the person is talking, you should understand that person. Why? I remember in one center I went to do some quality assurance. Unfortunately, they had a very, very wonderful machine that cost millions. But the man, he was almost stingy getting a very good AC for the system. So it is at your own benefit. If you don't get a good heat cooling system for X-ray, you are compromising the life of the tube because at times if the tube loading is so high, something can just impact, and then of course that would be penny wise and a pound foolish. Some of these things we need to know. Why at times we're going to have, why do we have so much ACs inside the city room? This blah blah blah, because of the nature of the city that needs to be seriously cooled. If not, we just say put on your machine, you want to work, the machine will tell you to wait for 1 hour. You can't do anything. You've got to wait. Of course, time is money. One has spent millions trying to procure this machine, but you don't have enough patience because the machine is not performing optimally. So we need to know all these things. That's why they have been added inside the syllabus for us to have some knowledge. And then the X-ray tube, X-ray tube. Of course, this is a very, very important portion of the X-ray tube, of the X-ray machine, the X-ray tube. An X-ray tube, of course, generally contains the cathode, um, the anode, the rotor, stroke, and the stator. We have the rotor, we have the stator, we have all the cable coils, the cables, and blah, blah. Yeah. So the major, then the support. The support. The cathode is the positive and negative electron. Where electron produce, you have the anode. The anode is where the electrons impinge upon. You have the rotor. Usually, this one is another type, a form of equipment used in rotating cathode. Because rotating, of course, rotating anode. When you want for some X-ray machines, for some X-ray tube that might lead, that must have this rotating tube. So on the rotor, of course, stator is connected to the rotor that provides the electric current and drives it front. Of course, we have the cables and the support. So these are the major, and of course, you have all of them enclosed inside and a tube housing that has been evacuated of air. It's a vacuum. The vacuum, of course, is there, like I told us before, because of um, the reasons we have stated earlier, so that we don't have unnecessary impingement or um, interference by air molecules inside. So that we are busy, everything has got to do with electrons going to the anode to interact. So these are the major components of the X-ray tube. And inside the X-ray tube, the current basically, the tube voltage. The tube voltage is normally around 40 to 150 kilovolt for general radiography. And then this is around 15 to around 40, 30 kilovolts for mammo. For mammo machine, and even photosynthesis machine. So these are the little. We don't need to go into so many details on this. Just know this as a positive electrode. So this a negative electrode, this a positive electrode. The rotor and stator, they are the ones that continually move. I think I have a diagram. Let me share this with us. This fast. I hope you can see that. We can see that. Okay. It's just the envelope, and that's in which everything is composed. This is the two ports. We have this is the anode. This is a glass envelope. Yes. This is the cathode. And the potential is usually maintained between the anode and the cathode. Of course, that is the power that drives the electron to the anode. And the electron, they come here, they knock on this, they impinge on this, and are decelerated. They are decelerated, and deceleration causes elements, photon. So this is the port where the electrons, the X-rays will be collected, we move from. So when you open this is the collimator. We have collimators here that now define collimators that define the field. So we have tungsten, the major elements. This is the starter. This is the rotor. This one's for rotating a tube. This one moves round. So at any point, at different points in time, the electrons from here, from this filament, this cathode, will impinge on different points on the anode. Of course, this helps in efficient heat distribution. Usually needed for some X-ray machines, or some X-ray, of course, machines like MCT, most fluoroscopy at times. But for mobile X-rays, we don't normally use it. They use a fixed or stationary X-ray tube. So these are just the simple things we need to know about it. Now we'll go to the cathode. So move to the cathode. That's our anode. We've done that. Let's go to the cathode. The cathode is essentially the negative, the electron producer. It is actually the filament, the whole component, the filament, and wherever it is connected to. This whole the compartment is known as the cathode. So the filaments is where the electrons are generated and stream towards the anode. And this one usually has two types in so many types of X-ray tube. We have usually two anode. Two focusing couples. So we have usually arranged this way. We have one small. It has a small focus, and we have another one big focus. Of course, this one they are usually selected automatically. So when we want to image maybe a thick patient which requires some big parameters. We want to have maybe around from 100 kV. You are using something like a 0.5 milliamperes, 0.5 seconds, 0.5 seconds. Of course, it requires a lot. So something just automatically switches to the big focus, but big focus. But when one is using some small parameters, this one is initiated. So in many X-ray production, in many X-ray tubes, we have two types of focus spot filament. You have the big filament and the small filament, and the big filament. Have told us that in the anode can be stationary or rotating. For stationary cathodes, we have it in some mobile X-rays, mobile X-ray unit, and the mobile fluoro unit. Actually, the CM fluoro. They normally use a stationary anode because we don't need these equipment are not used on a very, very busy schedule. We don't use them where we have a very, very busy schedule. But if you are in a big hospital, of course, you can't be using mobile X-ray, except for some specialized parts of the hospital where we don't normally use this one. Why? This one, for stationary, the cathode isn't, the anode isn't rotating. The anode is not rotating. So there's something, the elements will just be impinging, the electrons will just be impinging here and going down. This one is not rotating. After some time, you shut it down. You shut the whatever. So something continues to cool again. But for the ones that we normally use, for example for CT, in which you use so much energy, you can't afford to use fixed electrode, a fixed anode. It must be rotating so that the heat distribution will be very, very efficient. As it is rotating, this one will be impinging on different portions at different time. So the heat waves will just be, we will be distributing evenly on this. And again, another thing why we use tungsten for anode is tungsten withstand so much heat and crack, and withstand so much high temperature that we use an X-ray. And it can absorb so much. It can actually withstand without cracking, without denting. So it has apart from being a high Z material, which is favored, the ability for it to withstand high temperature is also another plus why we have it there. Let's see, something 74. Okay, we now go to another very important part. I want to look at the focal spot. Focal spot. Another angle first. All these are interrelated. Anode angle. The anode, maybe this is an anode. You have this one being a cathode. The anodes ordinarily should be this configuration, but it is not so. The anode configuration is not like this. The anode is tilted. Okay, let me have very small. The anode is usually tilted at an angle. It has its significance. Tilted at an angle. So if you have an X-ray coming this way, assuming this is an anode, we are going to have some form of electron just down this way. But it's tilted at an angle for a particular reason. The anode is usually this way. Usually tilted at an angle. At an angle. That angle here. At an angle. Mostly the angles fall from around 7 to 20 degrees. This is for the purpose of better heat distribution, better heat and loading. If this thing were to be straight down, this is the portion that we have the impact of this electron. This is the portion we get. This is the portion that we have the impact of this electron. On this electron, they will be impinging on this this point. But if we bevel it a little bit at an angle, this is the effective points that we have that we be interacting with the electrons. You can see this one from simple mathematics. This value, this from here to here, this is the hypotenuse. From here to here is smaller than this length. So because of that, we are going to have a better heat distribution here than if it were just 90 degrees to this. So that is why this one, the anode is tilted at an angle for better heat distribution on the anode. Because if we don't do that, of course, we might run the risk of having to buy so many things, having to the manufacturer having to, compromise the, what's it called? Might have to spend a lot of money to be able to take care of the heat dissipation. Of course, we normally have this heat dissipation. This one being connected to copper plate that is immersed inside a water, an oil bath for better heat dissemination. But then this is the major reason why we bevel it, because this one will offer a greater surface area for the electron, and as such, you're going to have a better heat distribution. That is one reason. Another reason is because of what we call what's it called, the this principle,
Line focus.
line focus principle. Thank you very much. Because of the line focus principle, because of the nature, the beveled nature of this is the effect. This is the actual focal spot. Focal actual focal spot. But at the end of the day, you're going to have something like this. The electrons. So this distance is effective focal spot. This line, this nature of tilting the focal, this anode, helps us to reduce this focal spot. The smaller this focal spot, the better the spatial resolution. So that's another reason. The smaller this focal spot, the better the spatial resolution of the imaging we are going to get. So this is another major reason why we have that. Because if we have the focal spot, so we have a relationship between the effective focal spot and the what's it called, the actual focal spot. The effective is simply the actual focal spot. Actual focal spot is effective focal spot multiplied by sin theta, where sin theta is the angle, is the angulation of the anode. Let's briefly share. Class 9. Oh my God. So this is it. So you have the cathode here. You have the true length. This is the true length of the beam, whereas this is the focal spot effective length becoming smaller. So this actually helps us to have a better spatial resolution. The more the focal spot we can get from a particular focal spot, the more the effective focal spot we can actually get from a particular focal spot, the better for us in terms of a spatial resolution. And that is why it is related to sin theta. We know sin theta starts from sin theta increases from 0 to the maximum 45, then 0 is 90. 0. So the maximum is about 90. So if you want to have the effective this thing, the angle should be less than at 45 degrees, usually less than 45 degrees. So that's why this is showing from 7 to 20 degrees as the best anode angles for a particular, for all the um, imaging equipment they're using X-ray. What is it? Effective focus point is the actual focus point multiplied by the anode angle. Okay, let me stop this and go to the another effect, very, very important effect that we have in X-ray, which is the heat effect. The heat effect is actually the reduction of the X-ray intensity, the X-ray energy towards the anode side of the machine. That is, the cathode side of the machine, electrons or photons emanating from the cathode side of the machine have more energy. They are more energetic than the ones at this other side of the machine, the anode side of the machine. Why is it so? It's so because we have okay, let's see. Let's see if we have electrons, how many of them coming down here, impinging on this anode. Some of them will interact here, some will go further down here, and so on and so forth. So because of that, we are going to have different energy distribution. The electrons that interact close here, When they interact, the photons emanating from there will travel through less thickness of this anode. So it will undergo lesser attenuation than the ones that travel down maybe around here, down here. They will undergo so much, the photons that will be produced from here will undergo so much attenuation. And apart from that again, because of the different distances, this one, look at, it still has enough, some amount of energy. But the ones here, they will have traveled a further distance before impacting with the anode here. So because of that, the electrons, the photons emanating from here, the photons here, they are lesser energetic because of their interaction. They have so much, they have interacted so much with this, the heel of this anode. That's why it is the heel effect. They have interacted so much with the heel of this anode. That's why they call it heat effect. But the ones around here that interacted around here, their maximum energy, they have more energy because we have a lesser interaction of the photons that would have emanated from the interaction of this electron with this. So we have so many of them. So the electron, that is why these are cathode area. The photons around this area, they are more energetic. So as you go down inside the anode, as you move down inside the anode, the beam, the X-ray beams emanating from there, you continue to have reduced energy because of the simple fact that the photons coming out from there are going to be much more attenuated than the ones around this area. It's a form of problem for in radiography, but it is also used to our advantage. You can actually use it to our advantage. Assuming you want to image a patient, a fat patient, of course. Maybe the abdomen, okay, okay. Just want to image the abdomen of the patient. You have this side thicker. All you need to do, this side is thicker. These are being thicker than this. This side is thinner. If you put this patient under this configuration, you are giving lesser radiation. A lesser radiation will be hitting this thicker part, while the more energetic radiation will be hitting this. So it doesn't give us a very good X-ray energy distribution, but rather if you now position the patient such that the the thicker part of the patient are facing, the thicker parts are towards the cathode area, whereas the thinner part are towards the anode area. Then of course you're going to have a kind of um, better energy spectrum of the X-ray as they impact, as they hit the patient, as they interact with the patient. So this is going to give us a better image, better energy discrimination than if we do it the other way around. So it can be used to our advantage. So nothing really, there is always a positive thing, even some things we feel are negative. So that's just the heat effect, the reduction of the intensity of the X-ray towards the underside of the beam. I think I should have another listen to share. That's going to share heat effect. Heat effect, heat effect, heat effect. So it's not here. Okay. I don't think I have the heat effect there, but anyway, that's an explanation on that. I'll quickly go to some of the components of the X-ray, of the X-ray tube. Some of the components of the X-ray tube. We have actually mentioned the major components of the X-ray tube: the cathode, the anode, the stator, the rotor, the cables, the support, the blah blah blah, some other things, and some other not too. These are the major ones. Then, based on that, we could we can further bring down these. We can further divide the whole X-ray tube into this component, the X-ray inserts, which is actually the cathode, the anode, the rotor. These are the major components. Of course, the support. Let's just stop at there. The X-ray inserts, the cathode, the anode, the rotor, stator assembly, then the support holding the rotor and the anode. Then the cathode is on this other side, connected to you by use of a cables to whatever we have there. So the whole of this is inserted inside the X-ray tube, X-ray tube envelope, X-ray tube and housing. So the whole of this insert is enclosed, is covered by the X-ray tube and housing, which of course, which also has the. Let me share this. We can have, we can always get all these images. Let me quickly. I was not time here. Okay, so this should. Okay, let's see. Okay. Now we can use this diagram. Oh, this one is not okay. Okay, let's use this. The rotor, stator, the anode, and the cathode. They form the insert.
inside the insert. This assembly and this assembly. This is the support. You have this the whole rotor, starter, blah blah blah. You have a support here, and this is not the comprehensive diagram anyway. So the whole of this is now housed using this. The whole of this is now housed. This is the envelope. This is the vacuum envelope, which can be made of glass or metal. Sometimes you can have it be made of the metal or be made of glass. All these they also even contribute to the filtration, some form of filtration. So we have lead shielding. This one, this is a glass envelope. After the whole of this is now enclosed in a lead shielding. The whole of this enclosed in a lead shielding, because we wouldn't want the X-ray is produced in all manner, scattered in all manner. Some coming here, even as we have even some backscatter, some moving up, so many places. So we have lead shield around this area that encloses the whole of this compartment, all of this compartment, so that no photon escapes except the one we want to escape from this spot. And because of that, we normally carry out a leakage exposure test when we are doing a quality assurance to make sure that what we have, the tube is not leaking any form of radiation. And it shouldn't be, even if you have any, because you can have a minimum radiation leaking from, it shouldn't be more than 100 milliröntgen per hour. It shouldn't be more than 100 milliröntgen per hour. And at least every hour, if you stay there every hour, you shouldn't have an exposure more than 100 milliröntgen. So the whole of this, inside the whole of this inside the tube housing, is actually what makes up these two, make up a tube, an IHU tube. Then we also have collimators like this. The ports, we have collimators around this port area. The collimators define the shape and the field size. If you want to image a very small portion, maybe you want to image the extremity, maybe the hand or the leg, we use a very, very small image, very small field size. So this port here that has collimators, the collimators X and Y have a parallel. They have two this way and two this other way. They define the field size. So the collimators are just this way. We have lead this way. I have another one this way. So this one they move this way, they move up, down, while this one move sideways. If you are moving this one this way, you are increasing this distance. So the image, you're having something like this. And if you are moving this one, something will be increasing this way. Something will be increasing down and up. And if one is moving here, you have this. So at the end of the day, these collimators, this one, they work together, this one also work together. At the end of the day, they are going to define the field size. So we also talk about filtration. These collimators also need to talk about filtration, which we have mentioned at one point or the other. Filtration. We have inherent filtration, filtration, and we have and filtration. The inherent filtrations are the ones which are there because of the components of the X-ray tube, like the X-ray tube housing, the envelope, the glass envelope or the metal envelope that houses the electron, that houses the X-ray tube.
big LEC. It offers a form of filtration. It filters the X-ray to an extent. Then we also have the mirror. We have one mirror inside the X-ray tube. There's a mirror inside the X-ray tube. We have a light source here. The light source, we put it on, it strikes the mirror here, and it comes out through the collimator, through the port. So this actually tells us because we can't see photons, we can't see X-rays. So the light helps us to say, okay, this is the shape of the X-ray coming out with the 2x3 or 4x10 and so on and so forth. So this mirror here also adds to the filtration of the X-ray. In the oil, because this thing is usually enclosed in the whole of this is immersed inside an oil bath, which helps us in disseminating and taking away heat. So it also helps us with a kind of filtration. Then we have added filters. These ones are the filters that have been, of course, this window here also offers a form of filtration, which is inherent. It also offers a form of filtration. Then the other filtrations are the ones we have purposely added just to bring about a very good energy spectrum of the Bremsstrahlung law. Those ones are usually chosen based on the type of machine. Some manufacturer might want to use, based on the output of their machine, they might want to use maybe 2 millimeter of aluminum or maybe 5 millimeter of copper, as the case may be, to help us eliminate those low intensity X-ray field. X-ray energy. I think somebody in either Kuwait or it's not Kuwait, I don't think, one of these Arab nations, they said they shared something with one of my colleagues. In their center, their X-ray machine they didn't know that there wasn't any filter inside the X-ray machine. It was when they were carrying out quality assurance, QA, and they started the HVL test, the H value layer, half value layer test, that they now discovered that the value they were getting very, very small compared to the values they should get for a particular range of energies. Then when they opened the X-ray, lo and behold, there wasn't any filter. So very, very important. Filter is very, very important so that we don't unnecessarily dose our patients. So we have the two types, inherent filtration and then inherent filtration and then added filtration. Then we have our X-ray generator. 22, okay. X-ray generator. X-ray generator, this is the powerhouse of our X-ray machine. Whatever we want to do is as a result of the components of the generator. The transformer, the rectifier circuit, whatever. Then you have the operator console. The operator console is where the technologies, the radiographers stay and impute those parameters. Those parameters, they will send a signal to the generator. Then the generator will sense it and say, okay, I need to do this and that. So the generator is the powerhouse of X-ray tube. It has so many components, so many both electrical and mechanical components, which define the X-ray beam we are going to get. So the X-ray generator actually operates from changes, of course, with the right equipment, changes the voltage from 400 volts to around 150,000 volts. How does it happen? How does it do that? It does that with the use of transformers, using various principles, electromagnetic principle. This is the highest you can get from whatever, or three-phase, whatever, and so on and so forth. A normal voltage we use at home, so from 200 to 220 for Nigeria. For some countries, we have something could be like US around the 100 to 110 for Britain. Also use this voltage range. So the highest you can get, maybe you are using a three-phase for industrial purposes, is 400. But the energy we want to apply, the potential we want to apply in between the cathode and the anode must be as large as this. How does that happen? That happens with um, the principle of electromagnetic induction, which uses a transformer. Electromagnetic induction. Electromagnetic induction. From a Faraday law of electromagnetic induction, that is, we even did that some, also did that in the MRI. That is, electricity can give rise to magnetism, and magnetism equally can give rise to electricity. So that's just the principle in a layman's language. Electromagnetic induction. Electricity can induce magnetism, whereas the magnetism can induce electricity. So that's the principle of electromagnetic induction. The energy we use at home is from NEPA is actually gotten from electromagnetic induction, in which we have whatever we're using, solar or whatever. In generating companies, they use one form of energy or the other to turn a turbine. So the turbine will now rotate in a magnetic field. We have very huge magnetic field. When it rotates in a huge magnetic field, electricity will now be induced. So that is the principle that the generators use. And then from there, we are going to give rise to alternating current. Alternating current. Current that changes its direction from one a particular cycle, it will change its direction twice. At a particular time, it is positive, and at a particular time, it is negative. So the generating power, the generating set of X-ray tube is going to give us alternating current. At the end of the day, this alternating current that has been produced, of course, is what we get from the mains, our mains, maybe 400 or 200. If we get so in designing if you want to design an X-ray, you want to get an X-ray, you want to know the type of electricity we are using there. If it is industrial, of course, we want to know the type of a transformer that X-ray machine has got to come with. If it is say 200 volts, we know the type of transformer that will transform 200 volts to 250,000 volts. So we all need the engineer has to know about all that in order to purchase at the right form of X-ray tube. So at this point, when the X-ray tube has been transformed with the use of a transformer, if you want to transform this from this, we need a transformer. So many of our equipment use one form of a transformer or the other. Can have a step-up transformer. You can also have a step-down. Like the ones we have on our street, those ones are step-down transformer. They step the energy down from, can be 33 kV or 11 kV. 11 kV or 33 kV. So our transformers, they step this. This is from our power stations. When they come, our transformers step them down to the ones we use at home, 240 volts. And the 240 volts, depending on if it is commercial, can be moved up using a three-phase distance to 400 volts. So we want to step up this. You're not stepping down. For the equipment we use at home, they have step-down transformers. And step this current, this voltage down from 240 to maybe 24 volts or 12 volts and so on and so forth, as the case may be. But we don't need this amount of energy, maybe in our laptops.
in our walkie-talkies, in our phones, and so on and so forth. They have transformers. Actually, the transformers are also built into all our chargers, all the chargers we use. So if you have your charger, if you connect your charger, you can actually touch the cable at the other end where you plug into your phone, because something has been transformed from the high voltage to the low voltage. So we have a generator. The generator does all that, all those transformations using a step-up transformer that will not transform it to the high voltage that we want to use in the X-ray production. And apart from that, even the generator is also responsible for the timers, the timer and the switches and so on and so forth. Assuming you want to image a patient, the you can set the selectable parameters, the kVp, the peak energy, kilovoltage. This one defines the energy. You can have the MA, the S, that's the MA is the ampere, that's the current. You use an MA because the current will be used mostly in milliampere. These are the selectable this thing that the radiographers usually input. And at times they might want to select maybe the bigger focus, bigger filament, or the smaller filament. But most times the machine does that automatically. So all these they are inside these timers. And at times you could have instead of this MA and S coming differently, at times they come together. MAS. So this one automatically, you are increasing this one might want to move from one value to the other. So these timers, they tell us if you set 10 seconds, because that's not possible using a video. You set 0.2 seconds. Immediately, you put on your, immediately one puts on the timer circuit. Immediately one puts on the timer circuit. After 0.2 seconds, something will just automatically go off, even no matter how long something is pressed. As if you are using AEC, automatic exposure control. If you ignite that, if you put it on, no matter how much you press, after the predetermined exposure has been reached, at least if you have the appreciable, when we would have gotten the appreciable exposure, something will just switch off automatically. So these are all parts of the function of the generator. Excuse me, just give me a few seconds. Sorry. Oh, sorry about that. I had to attend to somebody. As I was saying, this timer switches. The timer is a type of switch. I've noticed they, of course, are always together. They control these parameters. If you set the kVp at a particular value, it's the switch there will keep it at that particular value during that exposure. And some of these things we want to check their reproducibility, want to check their consistency, want to check their linearity by doing quality assurance schemes.
quality assurance programs. You can check the KVP reproducibility or KVP linearity, MAS reproducibility, and so on and so forth, to make sure that whenever you set a particular value, that value is going to be maintained throughout the exposure. So these are these works are usually done by the generator. Very, very important portion. In fact, the powerhouse of the X-ray tube of the X-ray tube. Apart from this, we want to look at the power rating. The power rating of the X-ray tube. We all know power from secondary school is the rate of doing work. So power is energy over time. Energy over time gives us power. We have P is simply energy over time. And then this power, electrical power, is given us as VI. So for X-ray tube, our power rating is actually the kV multiplied by the current. The current. This actually gives us an idea of the power of the generator. We want to know the maximum power that a particular generator is going to give us. We want to know this because this is going to guide us into the heat loading of the generator, the heat loading of the X-ray tube. You don't want to load the X-ray tube such that the tube will be damaged. The tube will be damaged. You want to control the rate of loading. You want to know how much heat a particular generator, a particular X-ray tube is going to accommodate. If the heat is not, the dissemination of the heat or the distribution of the heat is not efficiently managed, because the generator, the X-ray tube can easily pack, which is one of the major problems X-ray tubes have. We don't have a system in which the heat produced is efficiently disseminated, then we might have run into the problem of having to replace X-ray tube after just a few years. X-ray tube should last more than 10 years or so. 5, 6, 7, 8, 9, 10. Some can even last up to 20 years, depending on the usage. So if you have a center where we have so many, the volume of patients, the volume of people coming to use it is high, then it has to be used well by, of course, using some external cooling. You can't, of course, just rely on the cooling system of the machine, which uses oil baths, copper attached to the anode, and so on and so forth. We have to have our own heating, efficient way of dissemination of heat. So we look at the heat loading. So the heat loading is actually a way of telling us how much heat is produced for a particular exposure. Heat is a form of energy, because during the thermionic emission, the emission of the hydrogen, the thermionic emission of the electron moving towards the atom colliding with blah blah blah. 99% of the time, the electron collision leads to heat. So X-ray is a very, very inefficient machine. It is a very, very, very inefficient machine. Even about as inefficient as it is a very, very wonderful tool for imaging. So the 99% of the time, we have to worry ourselves with the heat and produce. And the heat produced is the energy, the heat energy is actually the kilovolt, the maximum kilovolt, the current as amperes multiplied by the exposure time. exposure time. So if you have these three variables, these three, they are going to give us to have an idea of how much heat energy is going to be produced for a particular. So at times, when you want to do some exposure, you select some parameters. If you press the button, nothing is going to happen because one has exceeded the heat loading of that machine. Let's say you go to the machine, assuming it's not using AEC, automatic exposure control. You just load, you just press, yeah, 2 seconds, current, 20 milliampere, kV. Of course, you can't select more than the the machine range, maybe 40 to 150. If it's 40 to 150, you can't select it. 30 cannot be selected. It's not selectable. Above 150 is not selectable. Let's say you select 120. Oh yeah, you press. At times, the machine won't answer if it has exceeded the energy, the heat loading of that machine. So this heat loading helps us to quantify the amount of energy at every point in time, at every exposure. Because as the heat is being disseminated, as the machine is continually heated, cooling also takes place. So the rate of cooling and the rate of heat production should um, be about the same. If not, you're going to heat up the machine and it might damage the tube. So that is why the, the we can't use the mobile X-ray for doing some very, very serious work or mobile fluoroscopy, like the ones they use in theaters, some makeshift, some theaters that are not purpose built. We just will just take the CM fluoroscopy there, you do it. Maybe have so many theaters, you can have ENT, you can have ENT theater, you can have what's it called? What's it called? Can have so many theaters for orthopedic theater, can have neurosurgery theater, and so on and so forth. You can use a particular CM machine, a CM fluoro, mobile, move them about, go to this place, go here, just to make sure one maximizes the use of what he or she had. So for that particular machine, CM fluoroscopy, it uses mobile, it uses some stationary anode. And because of that, we can't use it for an extended period of time. We just use it for a very short period of time. We put it off again. We use it for a very short period of time. We put it off again. But for the fluoroscopy machine that are dedicated to use for interventional procedures, of course, they must have a rotating machine just because of the problem. Rotating anode just because of the problem of the heat loading. So heat loading is very, very important in quantifying the amount of energy a particular machine produces. Oh, sorry, this is just about the best we can do with this topic. We don't have so much time again, so much time. Time is so short based on the belief that the exam will come by October. So we just bear with us. We have to rush this as much as possible. Now we want to finally look at some of the factors that affect X-ray production. Factors that affect X-ray production. We have a few of them. The X-rays we produce, the Brentano and the characteristic, we have so many factors that govern their production and their efficiency, both in terms of quality, that is how energetic the X-ray is going to be, or the quantity, how much photon we are using. Maybe you might be using for a particular exposure, maybe 150 million X-ray photon, so on and so forth. So we have some factors that
affect, that determine the quality and quantity of X-ray production. The first one is the anode target material. Anode target material. The anode this material for general radiography, the major material used is tungsten, like we've stated before. Why? Because it has a high Z material, and again, because it can withstand the high temperature. So it's seriously going to affect the type of X-ray that we produce. And because it has a high Z number, it's going to be efficient in the production of brain salon and even characteristic X-ray. So the type of X-ray anode target material is very, very key. It also tells us why we might not want to use tungsten for mammography. Though newer mammography these days have tungsten also as the anode, but most of them have the molybdenum and the rhodium and target. The ones that are used in tungsten are actually the ones that are used for, because when we get to mammography, differentiate between a screening mammography and what's it called? Diagnostic mammography. So the anode target material is one factor that determines the type of the quality and quantity, especially this one has to do mainly with the quantity of X-ray. So you're going to have many X-ray photons or fewer X-ray photons. But we want to also look at the tube voltage. The tube voltage also this one has to do with the quality of the quality in terms of energy. Quality is that which tells us the energy of a particular X-ray. If you have 70 kVp peak voltage of 70 kilovolts, what's this one? The production of the X-ray will be different from what you have for kV, 50 kV as the peak, because the exposure is actually proportional to the kV squared. I see the kilovoltage and squared is somewhat square of the voltage exposure. So if you have the more the kVp, the more the exposure one is going to have. So, but this one and the MAS, which we are going to look at, I think the MA, they are kind of interrelated. Because at times when you are increasing the MA, the kVp will be reducing. I mean, if increasing the MA, the timer will be reducing, except they are together. So we also have the tube current, of course. The tube currents. Of course, the more the number of time for a particular exposure, the more the number of photons that will be produced, and of course, the more this one quantifies the X-ray photons that they're going to have. Quantify that. Of course, this one also has a bearing with the time, tube current or tube time, the time which something is going to be on. So in most systems, you have it as an NAS. The ampere second coming together. The product is what the machine displays for some radiographic X-ray machines. They also could also have the beam filtration. the infiltration. Like we said before, the infiltration usually helps us in modifying the spectrum of the X-ray energy that's produced such that the smaller energetic, the smaller ones are gotten rid of. So we'll be left with the higher energetic X-rays that will be useful for production or that will be useful for imaging. And the generator waveform, the waveform of the generator, waveform of generator. This also has an effect on the type of the quality of X-ray we are going to have. As we have so many types of generator, we have a single phase, we have triple phase, you have so many manner of a waveform, so manner of a waveform, and have the generator. You could have the one that is fully resolved, fully rectified, and full wave rectification and the half wave rectification. I don't want to bother you with all that because the machine, the alternating currents that come out from these machine, of course, the alternating current from the mains of our houses, let's say 400 or the 200, blah, blah, blah. You now step this one up, you step it up to the value of kV we use, maybe around 200,000 volts. And you can have some idea like this. Then at the end of the day, we have very, very large waveform. So this is the one we need to rectify. We need to rectify these, but this is just oscillating. We don't want that. We need to rectify it just such that at the other cycle, so nothing will be read. So this portion will be left out. So just that we now have a current just flowing in one direction. So this is what we call rectification. It has been rectified into one particular direction. Then on this way, this is just a half wave. You could actually have a full wave rectification. So that instead for this one to just be up during the second phase, it will actually be reversed and you now have it this way. So this is for full wave rectification. I don't want to bother you so much with that. So all these things, they actually contribute towards making the generator, of course, which is eventually going to lead us, give the machine its output. It's going to lead us to the X-ray having a better energy output, so that you wouldn't have a kind of a defined form of energy output. It's different from the ones in which you don't have a very good rectification. So the waveform of the generator also helps in defining the type of an X-ray that will come out from the machine. Type of X-ray, how the energy is going to be distributed. Whether it will have a very good energy distribution, or we have the ones that wouldn't have good energy distribution. So the waveform of the generator is also another factor that affects that. But this topic is actually it's just a precursor. This explains, because we're still going to miss some of these things when we get to mammography, and we get to fluoroscopy, and we get to CT. We're going to again mention some of this point. So this is generally what we should encounter. We will continue to encounter in some of our equipment that they use X-ray machine for image information. And I said I should have sent the quiz, but I looked at the timing again, having to do quiz at every, especially for this. In this diagnostic radiology, we have this portion, X-ray production, blah, blah, blah. We have image, we have fluoroscopy, we have mammography, we have image quality. We also have CT there. So I'm still looking at a way of reducing the time we spend on the quiz for each section. So I'm looking at maybe after the end of, towards the end of this one, before we move into mammography and ultrasound, mammography and fluoroscopy, then I'll send the questions for this after we have finished the other topics. We should just go through the course outline, I mean the schedule, and then see the next topic. After the topic before mammography, or which one that comes first, mammography or fluoroscopy, then I think we now have a quiz so that we just try and see how we manage this time, because we don't have so much time with us. And from time to time, we'll be having some extra lessons to see how much we can catch up, meet up. So,
Excuse me, sir.
yeah.
Excuse me,
Yeah.
please. Can you go over these factors affecting X-ray production? As in, just
Okay.
go over them again and exactly how they affect, the X-ray production.
Okay. The anode target material affects the production of X-ray, in the sense that the lower Z, if you use a target material that has a low Z, for example, I use a calcium. Calcium is element 20. Of course, it's going to give you some X-rays, but the ones it will give you will be low energetic X-ray, low energy X-rays, which will not be useful for the purpose of imaging, because the energy that will be coming up from this calcium 20 will be low. They will just be absorbed inside the body, and they may not reach the detector. So, but if you use high Z material like tungsten, which is element I think 78, it will generate Bremsalon that have appreciable energy, and of course characteristic energy. X-rays that characteristic X-rays that have appreciable energy. So because of that, you are going to have so much energy from the X-ray tube, in which the anode is tungsten or molybdenum or even rhodium. Okay, rhodium. So they are going to give us a better energetic energy, which will be useful for the imaging purposes. Because all these things, we are not using it to kill cancer. We're actually using it for imaging. So if it's not energetic enough, the X-ray just travels some distance along the tissue. They just be deposited as heat or so, without reaching the detector, which is our main purpose. To be able to penetrate the tissue and get to the detector to form the image. Then for tube voltage has got to do with the quality of the X-ray beam. That is the energy of the X-ray beam. If the energy of the X-ray beam is, if you have a 70 kV, for most for general radiography, the energy is from 40 to around 150 kilovolts. If you set your energy, let's say you have a small patient, a pediatric, you wouldn't want to go high, because if you are going high, exposure is directly proportional. Exposure is directly proportional to kV squared. So if you are imaging a pediatric, you choose a kV that has a lower value, usually around 60 or so. 60 is 50, of course, 50, 60 kilovolts, so that you don't introduce so much exposure into the patient. So this is where tube voltage quality comes in. How energetic is the X-ray beam? If you are using lower kV, you're talking about lesser in energy X-ray.
If we're using higher ones, yeah, talking about higher energetic X-ray, which is appropriate for these patients or adults. In tube current, I can tube current affects the production, the X-ray, in the sense that the more the current, if you turn on the current for a long time, it's going to give you more photon energies, of course, directly proportional. The more the number of currents, the more the current, the higher the number of, the higher the current, the more the photons that will be deposited, the more the electrons that will stream towards the anode, they are going to the anode. Of course, it will lead to production of so many photons, so many X-ray photons. It has got nothing to do with the energy. That is, let's say you have selected KVP. You now turn on the machine for a very long time. It means you are using so much, you are getting a lot of X-ray. This is especially useful in fluoroscopy, the on time. Okay, it has to do with time. Of course, also current. So current, the more the current inside the tube, the more the exposure the patient is getting. Actually, this helps us in image quality. We're going to get to that. The more the current, the more the image quality. The more the signal to noise ratio, SNR, or even CNR, contrast to noise ratio, is going to be improved, but at the expense of those to the patient. So we want to get to a compromise between those and patient safety. And beam filtration. If you don't filter the beam from an X-ray machine, the lower energetic beams, which are not useful for anything, they just deposit inside the patient's body because they don't have so much energy to penetrate the patient and form and interact with the body and then go to the detector to be formed. Then it is a useless. So the lower energy beams are just removed. They've got to be removed so that we have high energy beams which are useful. Then for some things like mammography, you want to remove the lower energy beam, and even at times you have to remove the high energy beam so that the energy is in between around 15 to 40 kilovolts. So that's the energy we want for better contrast between the all those microcalcification and whatever that have a very similar contrast. We want to do that so that you have a better image, of course, a better image contrast. And beam filtration is there to help us remove, especially the lower energetic, the lower energetic X-ray beam, which don't contribute anything whatsoever to the image quality. All it does is because it can't move beyond the patient's body, they just travel a few centimeters inside the patient's body, and at the end, they're just deposited there. Nothing happens. So we need them high energetic ones and to penetrate the patient's body and then come out and affect the photographic plate, which will now form the image. That is what we are interested in. If you are not interested in that, then there's no need of having that. So the waveform, which is the physics or engineering of the machine, the generator, is another topic on its own. It makes use of so many types of a generator waveform. Want to have a single phase generator. We want to have a double phase generator. We want to have generators that use a full wave rectification or half wave rectification. Full wave rectification or half wave, half and half. So the one that have full wave rectification, they give us a better energy discrimination, energy component. Give us better energy so that we don't have just have a kind of a uniform energy. So the energy will not just be scattered if you want, let's say you apply the 70 kVp, or you are using 70 kVp. This is the energy, this 70 kVp, at the end of the day, the energy you might have will just be in between maybe 69 to 71. But if it's not fully rectified, you might have it from maybe 60 to 80. You can see that you have selected 70, but at the end of the day, you're having close to 60 to 70. It is still this 70 is still the average. So you see that this one is not too efficient, but this one is a very, very accurate, very, very precise to what we actually said. So these things, among other factors, are responsible for the X-ray emission and the factors that actually affect X-ray emission. I don't know whether I answered it.
Yes, sir.
Yes.
Thanks.
You're welcome.
Hello, sir.
Hello.
I actually think that these factors, the commonly asked question is relating it to the energy spectrum.
Okay.
With that curve that you drew initially, which you use the beam filtration to demonstrate,
Yeah.
some of these factors can also affect area under that curve. So the common question they ask is, how does this change that curve?
Okay.
Maybe there's no time now. I don't think we go into that.
And the major
We
thing
need
that changes the form of this state is the beam filtration. The beam filtration is the major thing that changes this state. Then anode target material also has a way of introducing those spikes there. If you use okay, no problem. If you use this waveform, this number of photons, this is the energy. If this is not filtered, if it's not filtered, you're going to have long that way. Or if it is filtered, you're going to have something like this, depending on where the filter is. If the filter removes maybe from the minimum to around 20 kV, there is something going to start from here. So remove from 0 to 20, you now have something like this. Yeah, this is the maximum energy. Let's say you are using electrons, you have applied the potential of 70 kV. So this one, the maximum energy will be 70 keV and as such. Then we look at after the two current, the only thing that this one will do to this curve is to change it so that you have more photons. That's how the two current is going to affect this one. Then the target material will affect in the such that, of course, the target material wants to tell us the type of material we're using. If you're using molybdenum, molybdenum has want to know the characteristic energy peak here for molybdenum, which is around 17 or so. Rhodium has its own. Molybdenum has its. Tungsten has its own. So if you know the energy, the absorption edge of those material, that is where you now put your spikes and so on and so forth. So that is going to tell us do that there. Then the waveform of this, you can't generally manage it there. 2 voltage, of course, the 2 voltage has got to do with this energy. The 2 voltage, the voltage is an 80. This energy here, the maximum energy here has to be 80. If it is 100, the maximum energy here has to be 100. The electrons, the X-rays or whatever, the X-rays coming out can never exceed this energy. So one should just be able to explain them in form with reference to this diagram. So that is it's. I don't know whether any other person has any other questions. Any other question to ask? Okay. I hope that is it.
Excuse me, sir.
Okay.
Please, sorry, this absorption edge. Can you explain the concept again?
Okay. The absorption edge has got to do mainly with photoelectric emission. You have photoelectric effect, which comes this way. It comes and decreases, so you increase in energy. As the energy continues to increase, the coefficient of this photoelectric emission coefficient. As the energy continues to increase this way, the probability of photoelectric effects happening continues to decrease. But as the energy increases, it will get to a time when the energy just gets close to the energy, the binding energy of this K shell. When it gets so close to the binding energy, immediately it reaches the binding energy of this K shell. What you now have, the energy is now able to dislodge this electron here. And if it dislodges it, we are going to have photoelectric emission. So that energy is the kh of the kh. It is give rise to a spike. It will lead to a spike in photoelectric effect. It will lead to a spike, an increase in photoelectric effect. And it will start coming down again. So as the energy is reducing, as the energy is increasing again, the probability of photoelectric emission will continue to decrease. At a point, you can have another energy which can have, of course, depending on the material, you can have two absorption edges, and so on and so forth. So this is actually, you can also, these are the edges, these are the absorption, whatever, absorption edges for different material. Let's say you have a particular material, you can have so many, you can have 2, 3, depending on the number of shell. This one falls, and this one goes out. You have a replacement, this one comes again, and so on and so forth. So depending on the number of transitions we have, we're going to give whether it is alpha or beta, alpha 1, beta 1, beta 2, and so on and so forth. So this is actually what is carried over here, the photoelectric effect.
Thank you, sir.
You're welcome. Actually, this is the characteristic portion, the characteristic X-ray portion. Whereas this other one is the Bremsstrahlung portion of the X-ray we are getting from the tube. Any other question? Okay. I don't know how it will. Today, Tuesday, tomorrow, Wednesday, today or Thursday. Tomorrow is Thursday. Okay, Friday. Salah, Friday. Can we have anything on Saturday? On Saturday? We might want to leave a lecture for Saturday because of our Muslim colleagues who might be involved in Salah merriment. We should leave on Friday alone and see whether we can have a lecture on Saturday.
Is there any Muslim in the group? I don't think so.
Is that what you think? I don't know, but I don't know. I don't know. But anyhow, let's see how it goes. We can have a lecture on Saturday or Friday, as this case may be. At this point in time, I want to sign out and wish us all. Okay. Wonderful holidays.
Thank you.
Thank you, sir.
You're welcome.
Thank you
Thank
very
you,
much,
sir.
sir.
Thank you, sir.
You're welcome.
Thank you.
You're welcome.